Hello everyone, Neural here, and today I'm going to start a new project that I'm pretty excited about. I'm going to make a 12-volt gasoline generator. For those of you who follow my channel, I do a lot of work with inverters, so I have a lot of inverters and batteries sitting around, and I want a way to charge these when the power goes out. So I'm going to do this. Now, there's a lot of videos out there about people who just take a gas engine, put a car alternator on it, and say, hey, look what I made. That's great, I don't have any problem with that, certainly, but I'm going to make my own video because that's just not my style. I like to be a little bit more thorough. Now, I'm not going to make a long, boring intro, so let's just jump right into it, and I'll describe things as we go. Here on the table are the majority of the pieces that I'm going to use to make this 12-volt generator. At its core, of course, is some sort of power source. In this case, I have a brand new Briggs & Stratton Vanguard engine. Vanguard is the top-of-the-line engine from Briggs & Stratton. It's a professional series, 3-year professional warranty. You should be able to get well over 1,000 hours of runtime out of something like this. Unlike the standard lawnmower type engine, where you can only get a few hundred hours out of it before they fail. Now, a few hundred may not sound like much when most people know that lawnmowers will last decades if you take care of them. Well, consider that you only run it for half an hour once a week, only during the summer. That's not very many hours. An automotive engine is significantly better. This is somewhere in between, but this is a commercial style engine. It's up there to compete with the Honda GX series, so it's very similar in that respect. It's a slant design, just like those, slant cylinder design. And I chose to buy this one because I had the choice at the time of 2 different engines that were on a very good sale. There was this one, a Briggs & Stratton Vanguard, which is made in Japan by Daihatsu or something like that. It's not actually Briggs & Stratton design, it's just outsourced to a Japanese company. But an engine here made in Japan, or a Kohler Command Pro, which is made in China. And I thought, let's see, China, Japan. I'll go with the Japanese engine. I later found out that this one, they're both overhead valve engines. This one has mechanical push rods, the other one has hydraulic lifters in it, so that other one may be quieter, but anyway, I went with this one. It should be a pretty good engine. I'm actually going to tell you what I paid for this stuff this time. I usually don't do that in my videos, but this engine cost me $200. It's a 182 cubic centimeter, 6 horsepower engine. More on those specifics later. For the alternator, I have this Delco Remy style 10SI case size alternator. This is brand new. I got this from a aftermarket company. It is a 105 amp alternator. I'll describe more specifically about the alternator later. I got a 10SI rather than a 12SI alternator. The 12SI has significantly better cooling capability. It can do about 50% more amps without overheating. I'm kind of skeptical whether this one is really going to be able to handle 105 amps. I'll cover that a little bit more later. I had other options for the alternators. Over here I have a Delco Remy 27SI series alternator that I could have used. This one's from a junkyard. I took it apart and had initially planned to convert this one into a 24-volt alternator to run my 24-volt UPSs, but I decided not to do that. And the bearings in this one are still pretty good. The brushes are still pretty good. There's a number of reasons why I chose not to use this. It is a 100 amp alternator, and it's in a larger case size, so it's designed to output a high current for a longer period of time. This one should be able to handle the load without overheating. I'm not so sure about the 10SI, but I also have this one sitting here. This one's actually a bad alternator, but this is a CS130, I believe, style alternator, and these are no good for this type of project. They are 130 amps, or at least you can get them up to there. This is like a 65 amp model or something, but you can get them up there, but they can't handle that. They'll actually melt, so don't use those. Use a standard type of old style 10SI alternator for something like this, and we'll find out if this can handle it or not. Like I said, I'm kind of skeptical. Now, to couple the engine to the alternator, there's a number of different ways to do it. You might think that a pulley is the best way to do it. After all, these already have a pulley on them, right? But there's reasons why I didn't want to do that. Instead, what I'm going to do is use one of these. It's a Lovejoy type coupler. It's very difficult to get an alternator to connect up to an engine properly. I'll cover that in more detail later, but this particular coupling has, well, it pulls apart. There's a rubber spider in the middle and a couple of jaws on either side. This one slips onto the engine shaft. This one goes onto the alternator. It's a special coupling for it. And some sort of mounting plate to hold the alternator to the engine. And this is what I have for that. It's made out of 1/8 inch steel. And the idea is you can just bolt it right up, and the alternator will sit here right on the engine. Oh, that's right. I also have miscellaneous mounting hardware in a bunch of different bags that I picked up from a hardware store. I forgot to mention this Jeep skid plate that I found in the trash. I'm just going to mount it to this for now. I may choose to mount it to something else in the future, but I didn't really want to mount it to plywood, so I'm going to use this. It's a little bit lighter gauge steel than I'd like, but it should work for now. Okay, let's talk some specifics. Why this engine? Why did I pick this one? Well, first of all, because it is a professional series engine, I wanted something reliable. So I got this one. This is a horizontal shaft engine. It's very difficult to properly mount an alternator to a vertical shaft engine. It's possible to do, very difficult to do properly. So I chose to do it this way with a horizontal shaft engine. It has a throttle control. It's not fixed throttle, which I specifically wanted for this, and I'll describe why later. It's 182 cc's, which is a very good size for this. I think 200 cc's is kind of the upper limit of what's practical. We'll find out in testing whether I'm correct, but that's what I believe. 160 gets to be kind of on the small side, and there's reasons for that with the torque curve of it. So this is advertised as 6 horsepower. Briggs & Stratton no longer advertises horsepower on their engines except the Vanguard series. They keep the horsepower rating on those. I don't know why, but they choose to. Now this particular engine comes in different horsepower ratings. I think it goes from 5.5 to 6.5, and it just depends on how they do the cam phasing and such on these engines, how their power curve looks. So if you graph out the power curve on an engine like this, and you get torque on the vertical axis and RPMs on the horizontal axis, normally the torque curve looks something like this. It peaks in the middle, drops off at the low RPM and at the high RPM level. And there's reasons they do this. They want some good pull-up torque on their application so that when the engine gets bogged down, it recovers rather than just stalling out. Because if you get past this top peak torque point, it's just going to tend to stall out. So you always want to stay on the right side of that curve. Anyway, a gasoline generator, for example, is designed to run at 3,600 RPMs all the time. So the torque curve tends to be more peaky on the top side. They still need some pull-out torque, but not as much. A lot of the other general purpose engines tend to have their torque curve centered around 2,500 RPMs or so. This is a little on the high side, 6 horsepower. I'd rather have something more like 5 horsepower in 182 cc's, because that would indicate that it has better torque at the lower range where I plan to run it. But anyway, this engine should work pretty well for that. I intend to run it at about 2,500 RPMs in this application, and it's part of the reason why I have this adjustable throttle. A note on coupling these to an alternator. Now, as I mentioned, it probably seems easiest to just use the pulley. It's already got a pulley on most alternators, especially these old style 10SIs, which are probably the most common alternator in existence. They're available everywhere, which is part of the reason why I chose this one, but I'm not talking about the alternator yet. Just the coupling method. You can put a pulley on here and use the pulley on your alternator. However, there's a major problem. The type of belt that these alternators use is a different kind of belt than what machinery uses. You cannot get an automotive style pulley to go on your engine, and you cannot get a machinery style pulley to go on your alternator. You have to do some sort of metal fab type work to get that combination correct. If you don't, your belt is just going to wear out and break in very short order, or you'll have other problems. Belts also have alignment issues. If you get it slightly misaligned, you're going to run into reliability problems. It's just not going to be a reliable setup. In addition, the pulley diameters that are necessary to make this work are very small. This is a 2-inch pulley, I believe, on here. And to get the RPMs matched correctly between your engine and the alternator, you really need to have about a 1-to-1 pulley setup. So this also needs to be about the same size as this. If you spin the alternator too fast, it gets very inefficient. I'll cover that later. So you need to have about a 1-to-1 setup to actually have it operate properly. And if you go through the math on 100 amps and go through the power curve and such of an alternator, you find out that you need to have almost 100 pounds of force on that belt pulling this away from the engine. Otherwise, your belt is going to slip. Now, 100 pounds is a lot. It's a lot more than the bearing load of an alternator is designed for. It's not good for the bearings on an engine. This happens to be a professional series one. It's specifically designed with a dual ball bearing for that sort of load, but most engines are not, and you'll run into early engine failure as well. And belts just can't take that, especially not these tiny little, I forget the series name, but tiny little alternator belts. They really cannot handle that. They'll overheat and break. So I really don't like the idea of coupling these with the belt. And really the curve of the alternator and the curve of the engine match up extremely well. So I'm going to run it at a 1-to-1 ratio. I have this Lovejoy style coupling that I bought from the Epicenter. It's a website. If I can pull this apart, I can show you. So it comes with this. It goes under your engine, along with the key. There's this rubber insert, the spider, that goes inside, and it mates to this side. And this is a special one that is designed to go onto a Delco Remy style GM alternator. Now, I don't know where else to get them, which is why I bought them from the only place that I could find that made something like this to couple to an alternator. I don't have the fabrication skills to make one of these myself, and it was embarrassingly expensive for these two pieces, the spider, and these mounting plates over here that I'll show next. It was around $100 for all of this stuff. It's a small company. I'm sure they don't make many of these. It takes money to keep something like that going, and really the quality of these seems pretty good, so I'm not going to complain too much. This particular one here, I think both of them, can't tell, yeah, this one too. So both of these are sintered couplings. They're not cast iron, so they're a higher quality one. And if you look on Grainger or some sort of supply site for these two pieces plus the spider, it's a very expensive assembly to start with. So really I got them for about the same price as a standard catalog, and this one is custom made to fit on an alternator, which will be really nice. Now, to mount the alternator to the engine, I also don't have the fab skills to do that, so luckily this website also sold the mounting kit for it, which are these plates here. One of them bolts up to your engine, like so. You put it on spacers so it sits off the engine a ways, and you mount your alternator to this plate. And this is part of the reason why I chose a 10 SI alternator rather than rebuilding that 27 SI, which I consider doing, because they don't sell a plate for a 27 SI. I'd have to make my own. I could do that potentially, but like I said, I don't really have the fab skills. Metal's expensive anyway, so this cost me about the same as making my own, and this is much better. I was a little bit concerned about the quality of these because they're not all that cheap from that website. But I was very happy to see that they're obviously fabbed by somebody who has the proper tools and who knows what they're doing. I'm not sure if it was done in someone's garage or not, but it's certainly professional, so I'm perfectly okay with it. This is 1/8 inch steel, nice and thick. They didn't say the gauge, so I was a little bit worried that it wouldn't be adequate, but this looks like a very nice mounting kit. Should work out pretty well. Keep everything nice and square and lined up. This sort of spider assembly allows for a few degrees of misalignment, but you don't want to misalign it much because this spider has to take up all that misalignment, and it will bend and overheat and fail with time. So align it pretty well perfectly and you'll be all right. Now, one of the benefits of coupling the alternator directly to the engine like this is, one, the shaft of the engine turns counterclockwise, and alternators have to turn clockwise, so you have to face them this way. You'll find some sites and some people that tell you that it doesn't matter which way they turn, they'll work either way. That is false. Make sure you turn it the correct way. There are multiple reasons for that, both electrical and mechanical. One, the brushes are designed a certain way. The brushes are not, the electric field in the alternator twists when it gets spun up at a fairly high speed, like when it's generating. And the brushes are offset somewhat to compensate for that. If you turn it backward, it won't output nearly as much or as efficiently. So you have to turn it the correct way for electrical reasons. Also, the mechanical reason, this fan, this is a backwardly inclined centrifugal blower. It has to spin this way. If you want to look that up, backwardly inclined centrifugal blower, you can look that up yourself and convince yourself, but if you spin it this way, it will not cool the alternator well at all, and it will be extremely inefficient anyway. So make sure it spins this way. It is absolutely necessary. The alternator that I purchased is not the best alternator for this application, but I had to get a 10 SI or 12 SI to fit on that mounting plate. 12 SI is the same mechanical dimensions, it's just a better alternator. However, I couldn't find a 12 SI from a reputable company that offered a warranty of at least 1 year. So I ended up going to the 10 SI. They're much cheaper anyway. And it has a 1-year warranty, so if it doesn't work, if it fails, I'll just return it. Hopefully it works out and doesn't overheat, but that's what this project is partially here to find out. They also gave me this performance curve. Supposedly this alternator was computer tested. They say that it does up to 113 amps. The regulator is set to 15 volts. I was disappointed to see that. That's too high. Should be around 14.7. Turn on speed 1600 RPM. I chose a 3-terminal alternator rather than the 1-wire type, so hopefully this is meaningless. 1600 is, I don't know, that's specifically why I chose the 3-wire alternator. Don't use a 1-wire alternator. I'm not going to get into that, but 1-wire alternators are junk. Don't ever use them. So if you notice the curve here, which is why I'm showing you this, on the bottom is RPMs. This is 2000, 3000, 4000 if you can't read it. Up here is current. This up here is about 113 amps. Down here is 0. So you see that at about 2500 RPMs, it reaches pretty well full output, which is about 90 amps. And I don't want to generate too much more than, see where this knee is in this curve? I want to be right in that range, otherwise the alternator just gets very inefficient up here. If you run a car alternator, a high output alternator like this, at the proper RPM, it actually is around 70% efficient. So the efficiency is reasonably good. If you run it up here, you're looking at 50% efficient. So you don't want to gear these things up. You want to run them right around here, 2500 RPMs. 2500 RPMs brings us back to our engine. That's why I have it directly coupled. 2500 RPMs works out very well for the engine as well. If you look at the performance curve of an engine, a fuel mapping of an engine, they're actually, most small engines like this are most efficient at around 2500 RPMs. They're also much, much quieter at 2500 than they are at, say, 3600, like a generator runs. So I intend to run this at around 2500 RPM. And it has a throttle, so I can adjust that if I need to, but that should work out pretty well. Now in terms of the displacement of this engine, if we take a look at our alternator curve, once again, I want to make sure that it has enough pull-out torque so that if it gets bogged down for some reason, that it has enough torque to spin the alternator back up. This line is steeper than a 45-degree angle on this graph, so I need to have sufficient engine displacement to do that. And I believe 183 or 182 cubic centimeters, what this one is about right for this alternator. It should be a little bit oversized actually, but that's better than undersized. And I don't think I can get more than about 100 amps out of an alternator like this anyway, a Delco 10 SI series alternator without overheating it, since it'll have to dissipate 600 watts or so of waste heat at that output. And looking at its construction, 600 watts is asking a lot out of a case like this. But we'll see, it's not going to be stuffed in a hot engine compartment or anything, so hopefully it'll work out. If it doesn't work out, I'm going to modify my mounting plate, rebuild this alternator, and put in this massive beast. This is a 100 amp Delco Remy alternator, so This should do very well. It's just big, bulky, and I don't have a mounting plate for it. I'd have to somehow figure out how to fab one up. I also want to note that these are made out of steel. You cannot make them out of wood. That won't work because they mount on the alternator like this. I don't know how else you would do it. And if you use wood to make it strong enough, it would have to be so thick it would clog up this fan and you wouldn't get any airflow. So it pretty well has to be metal.